The internet loves a robot that picks up a Lego brick from a messy pile in under 10 seconds. It looks like magic, but it often hides a dangerous fragility. When we move these demos into real factories or homes, success rates plummet because the training environment is too perfect. Today, we are going to expose why diffusion policies fail when they leave their simulation cages and what that tells us about building truly robust mechanical intelligence. The core of this problem lies in how current learning algorithms perceive the world. When a robot learns to pick a specific Lego block using a method like UMI, it is not just learning motor skills. It is developing a rigid coupling to training specific configurations. The system becomes so optimized for the visual statistics of its dataset that any deviation causes catastrophic failure. This creates an illusion of robustness where the machine appears capable until reality introduces even minor noise or occlusion. The evidence for this brittleness comes from recent research into vision, language, action steering, specifically studies like VLS, which analyze diffusion policy failures in manufacturing contexts. The data reveals that these policies do not fail because they lack motor dexterity. They fail because their internal probability mass concentrates on a single optimal trajectory found during simulation. In the real world, when friction varies or objects shift unexpectedly, this narrow focus prevents adaptation without retraining the entire model from scratch. This phenomenon can be described as brittle convergence. The diffusion policy assumes that the future state of an object is predictable based on its past training data. However, in a cluttered environment like a warehouse bin or a child's playroom, physics introduces variable latency and unstructured chaos. A block might slide unexpectedly while being grasped, creating a temporal misalignment between what the robot expects to happen and what actually happens. The policy cannot adjust because it is locked into an action distribution that assumes low latency stability rather than handling the chaotic reality of physical interaction. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. To understand why this matters for real-world deployment, we must look at how these systems handle out-of-distribution scenarios. Real-world evaluation shows that generalist policies trained on clean datasets fail to generalize when faced with novel object poses or occlusions. The diffusion prior is over-optimized for the specific visual patterns it saw during training. When a Lego block lands in an unexpected orientation, the robot does not recognize this as a new problem to solve. It sees it as noise that violates its internal model of reality. The industry has attempted to bridge this gap with techniques like steering mechanisms using vision language models. These approaches aim to allow robots to adapt to semantic shifts without retraining. Results on benchmarks like Calvin show improvements where these systems achieve a 31% gain in task completion rates compared to standard diffusion policies. Similarly, tests on the Libero Pro benchmark demonstrate a 13% improvement when facing unstructured environments. However, even with these advances, the fundamental constraint remains: the system still struggles to adapt seamlessly without significant computational overhead or data collection efforts. The challenge extends beyond just making the robot smarter in isolation. The broader industry faces a prohibitive cost associated with verifying that any of these improvements actually work at scale. Assessing policy reliability requires hundreds of physical rollouts because simulation alone cannot capture every edge case. Tools like AutoEval and SureSim attempt to mitigate this by correcting for simulation discrepancies, yet they only save 20 to 25% of hardware effort compared to pure simulation testing. This suggests that while we can technically build robots that handle complex tasks in controlled settings, the production trade-off remains a massive barrier to entry for chaotic real-world environments. This economic reality forces us to reconsider how we define success in robotics. A robot that succeeds 99 times out of 100 is often considered perfect in engineering circles. But if it fails on that last attempt due to a shifted surface or an unexpected obstacle, the system has not truly learned. It has merely memorized a specific sequence of events. True mechanical intelligence requires handling the unstructured chaos where physics does not follow a script and every interaction introduces new variables. The gap between learning to pick a Lego block in a video and performing that task reliably on a factory floor is defined by this lack of adaptability. We are currently witnessing a phase where diffusion policies excel at specific, high-reward trajectories, but struggle with the entropy of the physical world. The path forward requires moving beyond rigid coupling to training data and developing systems that can maintain robustness against semantic shifts without incurring prohibitive compute costs or requiring constant retraining cycles. Until we solve this fundamental issue of adapting to unstructured chaos, our robots will remain impressive toys rather than reliable partners for the real world. The technology is advancing rapidly, but the engineering challenge lies not just in making them faster or more accurate, but in teaching them how to handle the unpredictable nature of physical reality without breaking down when things go slightly wrong. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.